In the previous video on estimation, and specifically the method of moments, we saw that we could use matching sample moments to population moments to estimate parameter values for the distribution. Now in those cases, we just did matching the mean or matching the first two moments. But in fact, in theory, if this is working well, all of the moments would match properly. Now, of course, I wouldn't be raising this issue if that were always the case. So what we've got here, so I think of a Poisson variable, so Poisson count. If n is a Poisson variable with rate parameter lambda, then the probability that n equals a count, so a non-negative integer k, is e to the minus lambda to the k on k factorial. Now, the curious thing about this is that for a Poisson distribution, the mean and the variance are the same. They are both equal to the rate parameter lambda. So this is quite restrictive because if I think, for example, of a normal distribution, I've got one parameter that controls the mean and one that controls the variance. If I think of a binomial distribution, the n and the p, they give me ability to sort of a bit of flexibility to make the distribution fit dataset. Whereas here, there is one parameter and one parameter only. So if I have observations that truly are Poisson counts, then matching either the first moment or the second central moment should give me roughly the same answer. We already said that if we have a Poisson variable, the mean and the variance of this are both equal, and they're both equal to the rate parameter, in this case, lambda. So in theory, I should be able to match the first moment. I work out the sample mean, and that gives me, well, I can match it to the population mean, which is lambda. But I can also work out the sample variance, the second central moment, and that should give me another estimate of lambda, and they should be similar. Let's take a case here that if I take a set of 5 observations, 3, 2, 5, 4, and 3, which I start by saying these are observations from a Poisson variable. Well, one thing I could do is I could work out the first sample moment, add those up, divide by 5. 17 on 5 is 3.4. Or I could work out the second central sample moment, so add up the squared differences between each observation and 3.4. And when I do that, I get 1.04. So what this means is that if I matched the first moment, I'd think lambda was about 3.4. And if I matched based on the variance, matching the second moment, I'd think lambda was about 1.04. So those are wildly different estimates. One's more than 3 times the size of the other. So in reality, what this should be telling me is not, oh look, one of these is 3 times as big as the other, I'll pick whichever one I like most, but rather these are not likely, based on this small sample, to actually be drawn from a Poisson variable. If they were, then the two moments would be similar to each other. The fact that I'm getting wildly different values here tells me that this is much less variable than I would expect if they were a Poisson variable. So in this case, I'd probably go back and just check my model. Am I sure that I'm drawing from a Poisson distribution? Another thing to note is that just because we obtain a parameter estimate from a particular routine, I shouldn't necessarily think that that is the true value. So we give an example here that, for example, I know a coin is fair and people are given an unknown number of times to flip that coin. So they know how many times they have to flip the coin. Each person that does this flips it that number. It's just that I don't know what that number of flips is. But nonetheless, when people have gone away and they've flipped the coin n times, they report back to me how many times they observed heads. So all I hear is I got 3 heads, I got 7 heads, I got 4 heads, but I don't know how many flips there were. What I want to do is to estimate n, the number of flips each person did. So let's say, and this is because I'm too lazy to type out a different set of observations, the number of heads reported back were 3, 2, 5, 4, and 3. That if I do the method of moments applied to matching the mean, I say, oh, this is easy. The mean number of heads was 17 on 5 is 3.4. If people are flipping a fair coin n times, then the number of heads from that distribution would be expected to be 0.5n. So if I set 0.5n is 17 on 5, then my estimate of n by the method of moments would be 6.8. So although the method of moments estimates each coin was flipped 6.8 times, well, I don't know what the true number of coin flips was, but the coins were not flipped 6.8 times each. Maybe 6 times, maybe 7 times, maybe 8 times, I don't know, but it was definitely not 6.8. So don't just take an estimate which comes out of an estimation method and think that that has to be the real figure. So again, apply a bit of common sense as to what the parameters might be.